Hello, everybody. Welcome to the Virtual Developer Summit 2020. We are going to be doing a session here, which is the ArcGIS API for Python, a deep dive into the API. My name is David Vitale. I am a product engineer on the Python API team.
And my name is Changming. I'm going to co-host this amazing session with David here today. Shall we get started?
Yeah, let's get started. So we're just going to give a brief background about what the Python API is. The Python API is a Python library for spatial analysis, mapping, and GIS. It's a powerful, modern, easy-to-use Python library that connects to your WebGIS, but also has different local capabilities. Python API is made for automation, for data science, for GIS administration. Basically, if ever you want to connect to your WebGIS through code, through Python specifically, you would want to use the Python API. So what can the Python API do for you? Or what different demographics are we trying to serve with the Python API? One big customer of the Python API are administrators and DevOps type people. So the Python API allows you to connect to your WebGIS, whether that's a portal or an enterprise, and you can programmatically update and modify users, groups, and content. So let's say you wanted to go through all web maps in your organization and check for broken URLs. You could use the Python API to programmatically look at all the content in your portal, get the URLs, and use some Python networking libraries to connect to that. You can also manage users groups, delete them, all those types of things. Python API also works very well with your WebGIS with managing of data. So you can update a web map. As I said before, you can also add a new web map. You can publish a service definition file. You can publish a shape file. You can do all different types of data management in the context of your WebGIS. Python API is also really good for data analysts, whether you want to analyze imagery or do different location analysis. This is all sort of in the broader realm of data science. So you can use the Python API in a data science sense to interact with feature data and with raster data to make great maps and do different sorts of spatial analysis. And finally, the Python API is a Python API. So it's great for developers who want to use Python to create programs and scripts to automate different workflows. So that's the very basic introduction to the Python API, or the Pythonic representation of your GIS. Now let's get to the deep dive part. So the way that this talk is going to be structured is we are going to go through all the different modules inside of the Python API, try to get to as many as possible, and give you a very, very broad overview of the Python API. So what is a module in this sense? The Python API's root module name is called ArcGIS. When you install it, it's conda install ArcGIS, conda install -c Esri ArcGIS, or pip install ArcGIS. Inside of that ArcGIS root module, there are different submodules, like ArcGIS.gis here. There also is ArcGIS.features, ArcGIS.learn, ArcGIS.network, all different modules of the Python API. And we're going to spend time going through each of them to try to give you a broad overview. So to start out, we are going to start with the most very basic module in the Python API, which is ArcGIS.gis. So I am going to open a Jupyter notebook, and let's get started with some live code. So what you see in front of you here is a Jupyter notebook. A Jupyter notebook is an interactive document format that allows you to run Python code inside of a browser context. Normally, when you run Python code inside of a traditional IDE like PyCharm or Visual Studio Code, you're running Python code, you're interacting mainly with text. When you run Python code in a Jupyter notebook, you have a lot richer of output since you're running in a browser environment. You can have images, you can have inline documentation with Markdown and HTML elements. You can have different equations and sometimes even interactive JavaScript widgets, including an interactive map, which we'll get to later. So Jupyter notebooks are a great sort of document format to show Python code in a lot more of a visual and education-focused way. It's a very, very great environment. We love Jupyter notebooks here at Esri and on the Python API team. So let's get started. As we said, we're going to go through the ArcGIS.gis module, which is the first one. And this is the most basic import statement that you will learn to love with the Python API. which is from ArcGIS.gis, import our GIS class. This GIS class is a representation of your web GIS. So by making a new connection to an ArcGIS Online, you do that by creating a new GIS class. So you now have access to ArcGIS Online as an anonymous user. You can query different items and do a sort of subset of things that you normally could do in ArcGIS Online. The way most of you will probably be interacting with your web GIS is by authenticating with a username or a password. So here I'm creating a connection to ArcGIS Online, and I am connecting as my username, David J. Vitale. I'm going to enter my password. And just like that, I have connected to my web GIS. So from here, I am able to do a lot of the same things that I would be able to do in a user environment standpoint, which I'll get to in a bit. You also can connect not just to ArcGIS Online, but to an external portal. So we manage a portal here called the Python API Playground. So you can actually connect to that GIS, to that web GIS, by specifying the URL, the username again, and then typing in the password. And I am now connected to my enterprise GIS. So this object is my ArcGIS Online, and this object is my enterprise. So what can you do when you're actually connected to your GIS? Well, you can search for different users inside of your organization. So Rohit is the lead developer for the Python API, so I can get his user account from our organization, and I can get different attributes off of his account. So I can get his first name and his last name and other attributes on it. Now connecting to my enterprise GIS, I can do enterprise.users.search, and I can actually, instead of just getting one user, look through all of the users inside of my enterprise. So here you can see we have about 10 or 15 users in that account, and different users that are coworkers here at Esri or other accounts that we have. So this users variable is a Python list, as you see by the brackets. So if you want to get one of the users from that, you simply index into that user list, and you can pull out an individual user and view them. So that's how you use the Python API to connect to different users in your web GIS. You also can use the Python API to view the content that each user has. So by typing gis.users.me, that prints out the user that you're currently logged in as, which in my case is my lovely profile picture of me and ArcGIS Online. So gis.users.me gets my user account. And from there, I can do each item inside of all of my .items. So by running the cell, which is a Python loop, I can take every item that I manage in that ArcGIS Online organization, every item that I've authored, and I can view it inside of the notebook. So you see here, I have a file geodatabase, I have a feature layer collection, a web map, some CSVs, all the different content that I have managed on this portal, I can gain access to programmatically. Just like how you can gain access to a user's content, you also can gain access to groups programmatically and look at their content. So here I'm doing gis.groups.search. I'm able to search for all groups, in this case, groups from the past when we've done the user conference. And I can get a subset I can get one of the items from that group and print it out. And as you see here, we have an example group that we made last year. You can call .content on that group to print out the different content that's in that group. So I've showed you how to get content that is specific to a user or a group, but you also can query your WebGIS for content in a more broader sense, i.e. in searching for all content in your organization. So here I'm going to do gis.content.search, and I'm going to search for all items that have Chennai in the name, and I'm going to take all the responses from that search and display them. So as you see here, I have a lot of different feature layer collections, CSVs, even a notebook that is the results from my search. So I can do all this programmatically. I can even specify different item types. If I only wanted to look for web maps, say, I would be able to see all of the web maps in there. I can take a different subset. I can take a different item from that group and print it out, as you can see here. I also can gain access to who owns that item what is the snippet in that item, and I can even update that item if I am the owner of it. So all different ways that you can use the Python API to update, manage the content in your organization. You also can gain access, so switching gears a little bit, I'm now connected to my enterprise GIS, and I am going to look at all of the servers inside of my enterprise. So by calling enterprise.admin.servers, I can list all of the servers that currently are hosted on that Python API Playground portal. So as you see here, it looks like we have the one main hosting server, as well as a raster server and a geoanalytics server. From there, I can take that list, take the first item in that list, print it out, as you see here, just a single server object, which is our hosting server. And I can even list all of the services inside of that hosting server. And then I can even get one of those services and print it out here. So as you see here, we have the classic world city service. By printing out the .status on that service, I can see, oh, this service is started, and other information about it, including the statistics on that server. So you can see what the folder name is, say, what the type of it is. So in this case, this looks like an image server, other information about the services, the machine IP address that it's hosted on. You can even call .stop on the service to then stop that service. And if you call then world cities.status, you see that this service is now stopped, and you can programmatically call start on that service. Give it a second, and then you now see that that service has been restarted. So that was the GIS module in the Python API, a great way that you can use to connect to your WebGIS, manage users, groups, and content. So that was the GIS. The next one we are going to talk about is the Widgets module. So remember how I said how the Jupyter Notebook format allows you to interact inside of an HTML element, including with JavaScript widgets? Well, at the Python API, we implemented a sort of map widget that allows you to visualize ArcGIS layers inside of a map and do some spatial analysis with that map widget. I think it's very cool, and we're going to show you about that. So I'm in a new different notebook, and I'm connecting to my WebGIS, in this case ArcGIS, with the same username as before. I'm going to type in my password. And before, when we did gis.map, gis.content, now we're doing gis.map. So in this case, we are going to make a new map with a zoom of 4. So by running this cell and specifying the output of that to a variable, you now see we have generated a map inside of this Jupyter Notebook. Now this map is behind the scenes using the ArcGIS API for JavaScript, so it allows you to do some very dynamic and great things. You can pan, zoom, you gain access to dynamic scaling as you're zooming in and out, all the features you've come to love with the JavaScript API. You can do all that with your mouse, as I'm doing here, but you also can control some of that through code. So I have that USA map variable. If I call USA map.rotation, I am able to update the rotation programmatically. So not only can you use the mouse to interact with things, you also can use code to interact with things. But this is just a boring base map, not very exciting. So let's add some layers to it. So I'm going to do gis.content.get to get a certain item. In this case, looks like census data. And I'm going to call usamap.addLayer on that item. And I'm not just going to add the item by itself. I'm going to specify a class color renderer, and I'm going to have that class color renderer apply to the total population 10 field. So by running the cell, when you give it a second to run, if you look at the map has now updated to include that item from your WebGIS. So in this case, when you zoom in and out, you gain all the access to that feature. You now have access to county data at this zoom level. When you zoom out, you have access to the state data. Everything you've come to know and love from authoring of web maps from the WebGIS, you can do with the Python API. I can call usa.map.save. So in this case, this map that I have added something to locally, if I were to close this notebook, I wouldn't have access to this map anymore. But if I call .save, specify a title, a snippet, and some tags, I actually can save this and persist this as a web map on our WebGIS. So I now can open this in a map viewer, this item that I've saved, and as you can see, it is that exact same item that I have created, that I have added before with that same layer type on it. So that's all great for adding different layer types. You also can use the Python API to control the base map that you add layers on top of. So in this case, I've just created a new map of New York City, and I am going to go through all of the base maps that we support, and I'm going to just show you them. So we have a dark gray base map here that you can see. We also have a light gray base map, and then we also have, wait for it to load, a satellite imagery base map. So we have a lot of base maps supported out of the box for you. Dark gray, the satellite imagery one. We also have some third-party ones that we support, like the OpenStreetMap base map and some other types of things. So you can use all of these to author the exact map, control how it looks and what looks good to you. So you might have noticed inside of this map widget, this little button up here. So although 2D maps are great, by pressing this button, you actually can control not only just 2D maps, but 3D maps. So the Python API has native support for both of those map types. And it allows you to do a lot of really cool visualization that you normally wouldn't get to do inside of 2D maps. So first, I'm going to show you how you interact with that. So you call gis.map, and you specify the mode as being 3D. And as you see, I am now able to make a 3D map here. And just as before, how I can control it through the mouse, I also can control this through code. So I can specify the tilt, specify the heading. And when I scroll around inside of the map widget, those values are actually updated in real time. So let's say you're looking at a map, but then when you want to share it, you really want to know what this extent is, and you want this exact extent. You can print out that information, or even print out, in this case, USA map.extent, and you have the extent and the exact version when you had scrolled with it. So great ways to help you author different maps. But a 3D map by itself is not that exciting. It's only exciting when, in my opinion, you add layers to it. So I'm going to create a map of Zion National Park, one of my favorite places in the United States. I'm going to get an item from our WebGIS, which is the different trails in Zion National Park. I'm going to specify the center, and I'm going to specify the symbol to use to draw this. In this case, I'm going to use a line 3D, specify the colors, and then when I call map.addLayer, I'm going to say, hey, use this symbol that I have just used. And as you can see, using the elevation data of the underlying map, you're able to see a lot of the different canyons and different hikes that you do. This hike is one of my favorite hikes. It is called the Angel's Landing hike. Highly recommend doing it. You start out on the bottom down here. You crawl all the way up, you hike all the way up, and then you go on this very terrifying ridge, which has 1,000-foot drop-offs on each side. So don't tell my mom that I did this hike, but it's a very good hike. And you can see the elevation very dramatically inside of this map widget. One final thing to show you when it comes to 3D mapping is some hurricane analysis. I think this is a really cool way that you can do mapping in the Python API. In this case, I'm going to create a simple renderer just like I did before, specify the color, but now I'm going to specify the visual variables renderer part on it. What this allows me to do is say, hey, for the pressure field of this data, I want you to change the color from red to blue in values 950 to 1000. But then, so that's one way that if you look at just the color, you're able to see the different values in there. But also, I want you to, with the speed, change the value from 220 to 150, the different size of this. What this allows you to do is visualize on a map two different values at the same time. So if you look at just the heights by themselves and not the colors, you're able to visualize the wind speed. So as you can see, some of these points over here are lower than these points in time for the hurricane. And if you look at just the colors like this, you're able to see, oh, reds have higher wind speeds and blues are lower pressures. And looking at all of it together, you can see a rough correlation between wind speed and pressure. So a great way that you can visualize data inside of the notebook, inside of an interactive map. One final thing to show you, which is asynchronous widget behavior. This allows you to define a callback function and then run this function whenever you click on the map. So in this case, I specified a findAddress method, which is going to call a reverse geocode on the geometry that I have clicked on, and it's going to print that out. What this boils down to when you run this is now if I click somewhere in here, the point is drawn on the map, and I see a reverse geocode response of, oh, this is this point in San Diego. If I click here, I get a different address. Here, a different address, and it even looks up the location of where we're at, in this case, a Macy's. So, great way to use the Python API to have some asynchronous logic, so that way you're not running Python code all the time, but running it when you click on certain things. So that was the widgets and mapping part of the Python API. I'm now going to go into the features part of the Python API. And mainly, I'm going to talk about the spatially enabled data frame. So one of the things the Python API is very proud about is our interoperability with third-party Python libraries. In this case, we have, one of our colleagues has done most of the work, but we have implemented a spatially enabled data frame. So if you are at all in the Python data science scene, you know how much pandas data frames are used. Pandas data frames are a way for you to read tabular data like CSVs in a very easy to use format. So a lot of different data science workflows use pandas to interact with data. And pandas data frames are great, but they're not spatially enabled. If there's spatial information on the pandas data frame, the pandas doesn't know how to deal with it. Luckily, using the Python API, you can actually have a spatially enabled data frame, which allows you to gain access to the spatial components of your underlying data. So in this case, I'm connecting to my GIS. I am getting an item, a feature layer, and I'm going to query the results, which in this case returns a spatially enabled data frame of ages 45 to 50, and I'm going to display that result. So as you can see here, I have my pandas data frame printed out. It looks like a normal data frame, but you see here this shape column inside of your data. So since I'm dealing with a spatially enabled data frame, I am able to plot that spatial component using the widget that I showed you before. So I'm going to make a new map of the United States. And this data frame object before was saved to a df variable. So I'm going to call df.spatial, that's the spatial part of your data frame, .plot. And I'm going to specify that map widget that I showed you before. And I am now able to plot that data on a map. So you can see the very large benefit of being able to go from a tabular format and plotting it on a map. When you're inside a map, you can also click on a point and see the specific data for that point. So that's great and all, but let's go a little bit more in depth with the spatially enabled data frame, because it's a very powerful tool to use. So just like before, I made a map, and in this case, I'm going to take that same data. I'm going to call df.spatial.plot, but I'm going to add a lot more arguments this time. I'm going to specify the symbol type. I'm going to specify the symbol style, in this case, a diamond. I'm going to specify the colors and other parts of it to really customize the type of plotting that I want to do. So as you see, I am now able to control the outline color and the root color to create a specific type of point that can be controlled programmatically and looks nice to me. So this is using renderers, and renderers are a very powerful tool that you can use to create great maps. So we have a lot of different types of renderers that we support. We have a simple renderer, a unique value renderer, class breaks, heat map renderer, etc. So from here, I'm going to show you what some of these renderers are. So I've made a new map. I'm going to take that same data, but in this case, I'm going to specify the unique value renderer, as you can see here, U. And I'm going to specify the ST column. The ST column, if you remember from all the way up here, is the state column. So in this case, this subset we saw was only Idaho, but it's the 2-letter state code for United States. So I am going to call df.spatial.plot with a unique value renderer. And as you can see, all of the different points are showing up as unique colors for unique values. So all the California points here are blue, all the Arizona points are yellow, Texas is green, Illinois is yellow, but a slightly different yellow, etc. So this is a really great way to apply a simple renderer to the data you have without needing to do too much analysis. That is the essence of what I wanted to talk about. I'm running a bit short on time, so I'm going to rush through this last bit. If you are familiar with arcade expressions, you can specify arcade code from the Python API, and then using the spatially enabled data frame, you can plot this using the arcade code. And if you give that a second to run, you will be able to see the response of our arcade code, which is changing the colors based off of party alliance and different counties in the US. So as you can see, the spatially enabled data frame doesn't just work with points, it also works with polygon data. And yeah, that's it. I am unfortunately out of time, and I want to save some time to my colleague Chunming for her to go over her parts. One last thing was the way that you control colors inside the spatially enabled data frame is you use Matplotlib color maps. So by running arcgis.mapping.display color maps, you can see the different colors that you use to create different maps. So in this case, you can specify different color ramps for green, where lower is white and upper is white, with the middle being there. Or you can even specify different values where it's harder breaks. So this is a great way that you can control a lot of different colors for you to draw on your map. So I'm going to hand it over to my wonderful colleague Chunming, who is going to go through the rest of the modules. So take it away, Chunming.
Thank you, David. Now let's move on with geocoding. Geocoding, to most of the non-GIS professionals, might be the first door that opens their mind to the world of GIS, because geocoder is always translating one form of geographic information to another. For example, geocode method in the ArcGIS API for Python is translating address to location, while reverse geocode does the opposite. It's translating location, aka coordinates, into address. One thing to keep in mind is the credits being consumed by the geocode method or the reverse geocode method is the same when you do the same operation in ArcGIS Pro or the ArcGIS Online, which is usually 40 credits per 1,000 geocode operations. All right, let's take a look at the geocode method. What are the input formats that's accepted by geocode? You can pass in single line address or multi-field address or point of interests, etc. For example, you can pass in Palm Springs, California, the single line address, into the geocode method. And the operation is going to return you a list of results. As we can see here, the list of entries bring back you the matched addresses and sorted by the score of relevance. The best match always comes the first. For example, let's look at the first entry. It is a dictionary object that contains several key value pairs. The top two most important key value pairs are address. If you look at the value here, it's Palm Springs, California. And the second key of importance, location, which is pointing to a tuple of XY coordinates. And we can see the score of relevance for this first entry is 1,000. All right, besides single line address, geocode method also takes multi-field address. Say Palm Springs Tramway, we can read in the address in a multi-field format by specifying key value pairs of address, city, region, etc. And you pass in as input argument for geocode method. You then get a list of 2 entries. If we look at the 2 entries closely, we can see the first one is the best match. because it's the exact address of the Palm Springs tramway. And the second one is less relevant in this case. All right, some people might wonder, what if I have multiple addresses? Do I need to do a for loop and then geocode each one of them? Yeah, you can do it like that, or you can do it with a batch geocode method. For example, here you have 6 addresses. You just compose a list of all these 6 entries and pass in for batch geocode method. This operation is then going to return you the geocoded location for each of these 6 entries, and it only picks the best match for each one of them. For example, here, if we are only reading the location property of the returned entry, we do get the coordinates of all these 6 matched addresses. And then we can use map.draw to draw these 6 points on the map view. All right, so geocode method is translating address to coordinates, while reverse geocode does the opposite. The most commonly seen usage of reverse geocode is to put it in a callback method that interacts with Map Widget, just as what David has demonstrated earlier. So with user input, the callback method interacts with the geolocation that's been entered by the clicking operation, and then you get back the text of the address that you are querying for. I hope you have found geocoding module really useful and practical for your daily usage. Network analysis module, on the other hand, is going to be there and help you with logistic, daily operational questions as well. For example, business or public services might have these kind of questions. What is the quickest way to get from point A to point B? Or if an incident happened in the downtown, what are the closest fire stations that can respond to the incident? Or say, if you are opening a new restaurant in San Francisco, what are the service areas to be expected that would be covered by the restaurant? So these kinds of questions, we'll give it a name called network analysis problem set. And usually it contains routing, finding closest facilities, generating service areas, vehicle routing problems in the problem set. ArcGIS API for Python is here to help you solve all these problems. One thing to keep in mind is that underneath the network analysis solvers, we're actually calling the network analysis services that are hosted by ArcGIS Online or Enterprise, which will require you to have an ArcGIS Online account with network analysis privilege. And then your application or your Jupyter Notebook is connected to online. Also, when you are using these network analysis solvers, you are also consuming credits. For example, if you are doing a route planning operation, it's costing you 1 credit per vehicle route. For more information about credits consumption, please check out our developer's website or ArcGIS help document. All right, let's take a look at a daily problem. Say now we are in Palm Springs, and then we want to find the best route to travel from Palm Springs to Los Angeles. What is the best way to do it? Before we touch the find route method provided by the Python API, let's make sure we have the input parameters needed for the operation. So we have found this USA major cities feature layer that's hosted on Living Atlas. What we need to do is to compose a query criteria and then use feature layer.query function, in which we specify the where clause to be state in California and the city names in a list of Palm Springs or Los Angeles. In doing the query, we're actually getting back in the result a feature set with only 2 features, which are the starting city as Palm Springs and the ending city as Los Angeles. Now we have this input argument that's required for find routes operation. We can go on to input other optional parameters. For example, if you want to specify the time of departure during the day, do you have a specific time zone requirement, and so on. The execution of find routes is actually quite fast. It will take around 11 seconds. And then the result is a composite of output directions, output routes, and output stops. We can try to pass output directions component into a spatially enabled data frame. And then we can see these useful columns can be listed, including route names, time, distance, and driving directions in text. Or we can do a summary and try to collapse the long listing data frame into a single line, which is going to show you for this route from Palm Springs to Los Angeles. If you are starting at this time, you are going to end at this time. And then it's also going to provide you the total travel distance and total time elapsed. Besides showing the results in a table, we can also try to visualize the results on the Map widget. What we will need here is to define the styles and symbologies for the routes and stops. Also, if you think necessary, you can also specify the pop-up message for stops and routes. And then you initialize a map view object and add all the feature in the feature set of output routes and output stops onto the map view. So here you're actually seeing the route being drawn in the purple line and the starting city and the ending city in the same map view. As a wrap-up, we have walked through the workflow of defining what's the problem set and then fetching the feature layer or feature set from online or enterprise. Then we run the network analysis solver, parse the results in data frame, and then visualize them in map view. The workflow is more or less similar for service area generation. In which we are using generate service area function, which is also inside network analysis module. And the problem of finding closest facility, in which we're using, again, an NA solver, find closest facilities. So if you are interested in more examples or the use cases, please check out our developers website, which provides you step-to-step demonstration of how to run these solvers. Maybe you have already noticed, what we have touched so far is only vector related, which means we're merely dealing with polygons, polylines, and points. What about raster? ArcGIS API for Python also provides you the raster module that contains classes and raster functions that are needed to handle raster data and imagery layers. For example, in terms of accessing an imagery layer, we can take advantage of the GIS module, the one that David has demoed before, and then we do gis.content.search, specify the title name of the imagery layer, and then make sure you have also specified the item type, which is imagery layer in this case. And then you can get back a list of matching imagery layer items. Or say if you have the exact item ID, that's even more straight. You just need to use gis.content.get and input the item ID. Then you get direct access to the variable reference to the imagery layer item. All right, now we have accessed the imagery layer item. What about visualization? First way is you can do layer item.layers and then you specify the index number. By querying the sub-layer directly, you get a static image, which is the screenshot or the preview of the imagery service. Or the other way, you can use add layer method and add the imagery layer directly into your map display, which will look like this. Besides raster data, raster functions are also published along with the imagery layer. So one kind of raster function is the server-side defined raster functions. You can do image layer .properties.raster function infos, and then you can get back a list of supported function names, including color infrared, geology, natural color, etc. Say if you are interested with color infrared image because you want to highlight on the vegetation biomass. What you need to do here is quite simple. Just import the apply method from ArcGIS Raster Functions module and then input the imagery layer item as the first input argument and the function name that you desire for, in this case color infrared, as the second input. And then you get the color infrared layer. You can also add the layer into display by using add layer. Then in the output cell, you are going to see this color infrared raster function being applied to the rendering rule. Another type of raster function is the well-known raster function. For example, in this case, we try to apply an Ndvi raster function onto display. Ndvi, short for Normalized Difference Vegetation Index, is usually doing a raster formula that's taking two bands, one as near infrared and the other as red channel, and then it's performing a normalization between these two bands. You can either define it yourself using raster calculator, or you can use this pre-built Ndvi function. Just a single line. You import Ndvi from Raster Functions module, and then call it with the raster parameter and also the band indices you want to apply the formula with. In this case, you pick channel 5 and channel 4. And then you will see the Ndvi raster function being applied in the render rule again on the map display. Besides using raster functions one by one, we can also do it in a chain. In this case, we're chaining an Ndvi function to a remap and then to a color map, which is a 3-layer structured raster function chain. In this case, we are getting the enhanced Ndvi result directly onto display. Also, we can call draw graph to see what are the workflows being contained in the chained raster function. Then again, if you are not satisfied with the layer just hanging around in memory or being an intermediate result as a variable, you can also do imagery.save using save method, which would then save it as a persistent imagery layer on your enterprise. All right, now we are more familiar with raster module. We can go on with the ArcGIS.learn module, in which case ArcGIS API for Python is trying to provide users with this end-to-end deep learning experience. For example, one of the most commonly used scenario is land cover classification. Say in the Kent County, Delaware, we are given an aerial image of the county. And then only for a small area, you can see some scattered feature class labels for lakes, trees, urban constructions, etc. for the pixels. And then you are given the assignment to train the model and apply it to a large area. So in this case, we are trying to predict the land cover class for each individual pixel. It's an image segmentation problem. What would be the steps to solve this problem? Before we go through the implementations, let's take a quick look at what the steps will be included. We'll first need to extract the training data from the small subset, and then we need to train the model, in which case we will be loading a pre-built UNet model. We are going to find the best learning rate. We're going to perform model fitting and perform prediction. At the end, we're going to deploy the local model and then perform inference. All right, let's get started. As mentioned before, we are handed with two input variables. One is the large imagery of Kent County, Delaware. In this case, we are choosing the NAIP imagery, which is hosted by Living Atlas. And then also we have beforehand manually labeled some of the features, say the trees, the urban constructions, etc. And then we have shared the feature class onto our own enterprise. And then here we are accessing the reference of the label layer. All right, now we are ready to go on with step 1, export training data. The export training data method in the ArcGIS.learn module actually does two things. It divides the large input image into sub-images, aka chips, and then it's generating single labeled image for each chip. Looking at the input parameters, we can see it requires you to input the raster image, which already have, and then the input class data, which are the manual labels we created, and then the output locations for where to put the exported samples. And the rest are just optional parameters like the format, the tile size, the stride size, etc. Running the cell, we are going to export the training data into a local folder. And then the second step is to load the local folder into memory. So we are using prepare data to load the exported samples into memory and divide them into batches. Here, we are using show batch method to show some random chips that has been prepared. All right, now we're done with data. Let's move on with the model. UNet image segmentation model is the most popular one in the current machine learning field. Instead of you defining the architecture yourself, you can also use this pre-built model that ArcGIS API Python has already brought to you. What you need to do here is just use UNet classifier constructor and input the exported data that we have done in the previous step. And boom, you get the training model ready. And then we go on to find the best learning rate. In this case, we're actually looking for a point where the loss is decreasing the fastest. Let's assume this turning point is around here. After we get the best learning rate, we can then use it in a model fitting method, model.fit. Besides learning rate, we also have to specify the Apics, aka number of cycles to be used for training the dataset. We are using 10 here as a beginning point. You can always increase it if the result feels like underfitting. The whole process is taking more than 11 minutes. And then we can see as the Apics increases, the accuracy also increases. And we're having fewer loss here. Now we are done with model fitting. Let's take a look at how the results actually are. Here we are using model.showResults to compare ground truth to the predictions. Ground truth on the left and prediction on the right. We can see from the comparison of these chips, most of the chips are looking quite good. Maybe except this one. But overall, the model has done a pretty good job in identifying the class types. We are now done with training from the smaller subset. Let's go on to deploy the model onto our enterprise. So we are using gis.content.add here to publish it onto the enterprise. And then we're getting the reference of the model package we just published. With the reference to the model package, we're then calling classify pixels to perform model inference and apply it to a larger area. So again, we have to input the target imagery layer we want to apply on, and then the model item that we have just published and shared. Running classify pixels, we are then getting the final results as an analysis imagery service item. One way to validate if this model is working correct by model inference and being applied to a larger image is to add the result imagery service onto map display. And we can see it visually to see if the model is working fine. So now we're again initializing the map view of Kent County, Delaware, and we're adding on the classified results onto display. Also remember, we have to apply a color map in order to see different feature classes displayed in different colors. For example, here, water in blue, urban construction in red, trees and forests in green. Looking at it briefly, we would say the model is doing a pretty good job, isn't it? Okay, I hope you guys have found ArcGIS.learn module quite fascinating, and it is doing a good job in bringing the end-to-end deep learning experience to users.
Great. So we are unfortunately out of time, but we'd like to thank you all for tuning in to our great session. To gain more information about the Python API, you can go to our landing page, which is developers.arcgis.com/Python, to gain all information about how to install the Python API, some guides and samples to help you get started, really everything you need to know to get started. And also we have a GitHub repository, github.com/Esri/ArcGIS Python API, where we post this PowerPoint and some of the notebooks that we have showed you today in the conferences resources branch. Here's some more information about the specific notebooks that were there, but if you enjoyed this talk, please go find the resources on our GitHub repository or visit the developers website. And yeah, thank you very much for tuning in.
Thank you so much for joining us.
Thank you. Bye-bye.
Bye.